All right. Did anybody think of any questions from last time or anything? Main thing that we did last time was get to the polymer partition functions, and then today and for the next couple of meetings, we're going to talk about basically different ways of attacking those things analytically. And then depending on how long we want to carry this on, we'll maybe get to numerics at some point. But all right, so before I dive into the field theory stuff, I do want to remind of I just want to remind of a couple of math properties that we're going to start using a lot. And I want to be able to use them kind of without too much comment. So I just want to write them down and remind them real quick. The first one is a really basic one. So the definition of an even function, we will use this. And so this is, of course, just that f of x is equal to f of minus x, right? So something that's symmetric about the y-axis. And in particular, Gaussian functions have this property, which is where we're going to use it. And that'll help us clean up a lot of things. And then there's a couple of Fourier transform, or a couple of properties of Fourier transforms that we will use. The first, hopefully you remember that the convolution integral. So we have an operation like this where one function is convolved with another one. We can write this as the inverse Fourier transform. So when I do like the really curly f with the -1, that's the inverse Fourier transform operation of the Fourier transform of f times the Fourier transform of g. And again, because you have things inside the integral that depend on r and r prime, but you're integrating out r prime, so the result has to depend on r. And so that's, again, something that will come up quite regularly. And then the last one is that you can write the integral of a product of functions, f of r, g of r. You can write this in terms of the Fourier transforms by summing over all of the wave vectors, or the possible allowed values of k. And this is f hat of k, g hat of k. All right.
Hey, Rob, I'm just going to chime in from Zoom. If you could move the camera a little bit to the left.
Yeah, thank you.
Oh, other way.
Other way, yeah.
There we go. I think that gets everything.
Okay. Yeah, thanks for catching that. All right. All right, so again, these are things that are going to come up quite a bit. And then what I'm going to go through today is basically how I figured out how to do the approximation that we're going to do for the homopolymer partition function. And then we'll sort of highlight the differences that you need to keep track of to do the block copolymer. But we'll skip some of the details on that. So remember, we're thinking about polymers in fields. And so we're going to say this is the homopolymer molecular partition function. Right, and this is what we worked through last time. This thing has a functional dependence on a field W that's some spatially varying thing. And generally that's going to be determined by its interactions with the other molecules. And last time we went through how we can write this basically as an integral over the positions of all of the monomers for the chain. And I guess formally we have n+1, though. Another thing that's going to happen today is we're going to start thinking about the large n limit. And so the distinction between n and n+1 is going to become kind of meaningless. So I'll be very lazy and sloppy about that. And so it's integral over all the monomers. Then we had e to the minus w of the nth monomer. So the interactions of the nth monomer with the field. The thing that we defined last time was this bond transition probability, which is the normalized Gaussian bonding potential between monomer n and n-1. Then e to the minus w, r n-1. And then keep multiplying this stuff together until you get to the end of the chain, where we had phi r1 minus r0, e to the minus w, r0. Right? And so again, all of the molecular information is buried into this object. And what we're going to do today is work through how we can approximate this really at the quadratic level in terms of the field fluctuations, right? And the way that we're going to do this is we're going to say that our W of R is going to be some part that doesn't depend on position, right? So this is going to be generally the homogeneous mean field value. And then we're going to assume that there's some spatially varying deviations around that homogeneous mean field result. And so W star, this would be the homogeneous mean field solution. And then right, these are going to be spatial variations around W star. And we're going to assume two things about this epsilon. First is that epsilon of R assumes small. And we're also going to assume that it has a zero mean, right? So whatever fluctuations we have around the homogeneous mean field, they're going to be on average zero, right? So if it's zero mean, that means that epsilon, the integral of this guy is zero. All right, and so then with these assumptions, right, so this is our approximately equals thing. Now we're going to come back over here and figure out how to simplify this whole thing. You have a question, Josh? Mm. The only thing that gives me pause is that maybe if you had like, but you're getting at a point that's always been a little bit unclear to me, and that's one of the things I haven't like dug into to really sort out. The one case where I think it could be a little funny to do it that way is if you had like a binary blend where the W minus field, and if the compositions were not symmetric, like if it was like a 40-60 mixture instead of 50-50, then I could see the inhomogeneous solution not being symmetric. But I'm actually a little fuzzy on that. And I don't think it's going to matter in what we're going to do. But yeah, well, all right. So we're going to take these two things and plug them into Q. All right. And so again, we have n exponentials of this thing. And each one of them is going to give us an exponential of a constant and then minus epsilon. Right. And since those exponentials of a constant is also a constant, and the product of exponentials are all become addition, we can pull that constant out as a prefactor. That'll just show up as a prefactor of scaling the whole value of Q. And so what we get is minus n W star over V as a prefactor. And then we have the same giant integral operation, but now with all the W of R's replaced with epsilon of R. And I'm going to drop back into the more abbreviated notation that I started last time, where the subscript indicates the R dependence. And so we have e to the minus epsilon. Oh, no, not that yet. And again, I'm already dropping the +1 on the n here. So if there's a little bit of a discrepancy there, that's where that comes from. But so I'm you know, there should formally be an n+1 here and an n+1 here, but we're just going to ignore that going forward. All right. Okay, so now we have exponentials of epsilon, and we're assuming that this epsilon is small. And so whenever we're doing physics or engineering and we say that something is small, that's the world telling us to do Taylor expansions. So we're going to do Taylor series expansions on all of those exponentials, right? And so that's going to become a headache pretty quickly. So we're going to have basically Taylor series expansions for each one of these n exponentials, and we're going to keep them up to quadratic order. All right, so this is going to be, and I won't write out a ton of them, obviously, but so this thing over V, integral dr to the n, and then this guy is going to become 1 minus epsilon sub n plus 1/2 epsilon sub n squared. And then there's higher order terms that we're going to throw out. Phi n minus 1, 1 minus. And this keeps going all the way up to the contribution from the other end of the chain at s equals 0. Okay, so now we have a whole bunch of multiplication to think through. And again, this is a bit of a headache. One of the convenient things that we get, though, and again, well, let me back up a second. So again, as I said, what we want to keep is up to order quadratic terms in the magnitude of the field, right? And so we see where there's quadratic terms that show up of like n multiplied by itself. And the other place where we're going to get quadratic terms is where we have epsilon n multiplying epsilon n minus 1, right? Anything that shows up as a linear term, we can throw away, right? Because the integral is 0, right? So because the integral of anything that's just linear in the epsilon n is 0, we can get rid of it. And then when we do all this multiplication out, anytime that we have like an epsilon n squared times an epsilon n, we can also throw that away because that's too high order in epsilon. All right, so the ones that we have to keep are all the cross terms and the ones that are squared. Okay? And so what we get, so again, we have the same prefactor over V, integral dr n. And I'm going to, again, abbreviate some notation here. So this capital phi, again, just so I don't have to keep writing them over and over again, I'm going to say that this is dn minus 1. It's just the product of all of those bond transition probabilities, right? And since these are just like scalar functions, they're not operators or anything like that, they commute, we can just lump them all into this one thing that we don't need to think about briefly. We will have to come back to them. That's why I'm not just throwing away. All right. And then the thing that survives from this multiplication, so you see that we have a 1/2 epsilon n squared, right? And there's a 1/2 n minus 1 squared, and we're going to have that type of term for all s. And each one of those has a 1/2 prefactor. Then the other thing that we have are these terms that start off as linear, where we have epsilon n, n minus 1. We'll have n times n minus 2, n times n minus 3, all the way down to 0. Then we'll have another sequence of terms, n minus 1, n minus 2, all the way down to 0. And so basically, we're going to have one of these products that'll naturally arise for every possible value of the subscript, right? So for every combination. And so the way that we can write this a little bit as a shorthand is that since that multiplication would give us, since that multiplying everything out would give us one combination of each pair, or each combination of S, we can get two combinations, write it in a way that we get two of them, but then just divide by two. Right, so we're going to say that this is 1 to n. Right, so this notation would give us a term that has both n times n minus 1 and n minus 1 times n, but then we divide by 2 to account for the fact that we have two of them. And then it naturally gives us the right thing for the diagonal term where m is equal to j. All right. Y'all okay with this step? So I skipped a lot of simplification algebra stuff there. All right. Okay, so the next thing we can do is, so now we have integral times all the bond stuff, and then times two different terms. So we can deal with that real quick. So we will have still same prefactor, W star n by V. Did anybody see what we're going to get from the 1 when we distribute the integral and the bond transition stuff? Close. It's just V, right? Because we have, this is where the distinction between like n and n plus 1 matters a little bit. Because remember, we have n total bonds, but really we should be integrating over n plus 1 coordinates. And the integral of all these bond transition probabilities is just 1. Right, so we do all of the integrals but 1, and that gives us a whole bunch of 1s multiplying each other. And then that last integral is going to give us a factor of V. Is that good with that? Hopefully that's consistent with what we said last time. All right, so that gives us just a V in place of the 1. And then we still have the integral and the double sum, and that's going to be the thing that we have to deal with next. So plus 1/2 sum over m, sum over j, integral dr to the n, all the bond transition stuff, and epsilon m, epsilon j. Right. And remember, those subscripts represent the dependence on the position of a specific monomer on the chain. Right, so whenever m is equal to n, that's the functional dependence of Rn. Right? And when j is equal to 0, that's a functional dependence of R equals 0. All right. All right, so this is where when I was trying to learn this stuff, I got stuck for quite a while. And the way that I figured this out was to just like pick a relatively simple version of this and just try to brute force it. And so I'll show you 1 or 2 terms of that, or show you how I got to it, and hopefully get to the point where we can at least recognize the pattern that will emerge. So let's just focus on this guy because that's the messy part that we need to deal with now, right? And just for the sake of, making something that's not trivial but is still doable, we're just going to work on that term. We're going to work on the underlying term for the case where n equals 5, right? Just something where there's a handful of monomers. It's not completely trivial. Not everything is a chain end, but it's not completely overwhelming to write it out either. All right, so we're going to say that this is n equals 5 monomers. And so that means 4 bonds. So this will be 1/2 sum over m, sum over j, integral, and I'm going to obnoxiously write out all of the terms. dr1, dr2, 4, dr. Right, so we have to integrate over the position of all 5 monomers. We have bond transition probabilities for all of them. And then epsilon4 and epsilon m and epsilon j. Actually, I'm going to make that R dependence also explicit. All right. And so again, we still have something that's kind of messy because we have this stupid double sum. So I'm again going to pick out one of the terms from this double sum, and we're just going to solve that because that will simplify it to the point where we can actually at least argue for the pattern. All right, so one term in the double sum right? So we're going to pick, and again, I'm just sort of arbitrarily picking things. I'm going to avoid picking a chain end, but other than that, I want something relatively simple. M equals 4 and J equals 2. All right, so that's, again, one monomer in from the chain end on both, and they're not bonded directly to each other. And so that'll let us see what some of the patterns that emerge in this, and hopefully just write down the answer. Okay, so once we pick that term, then what we have is 1/2 integral dr. Just going to write it as dr to the 5th for now. And I'm going to order all of the terms that we have. So we have integral 5, 4. Sorry, bond transition between 5 and 4, bond transition between 4 and 3. I'm sorry, I want to put epsilon here. So we'll say this is epsilon 4, bond transition 4, 3, bond transition between 3 and 2, epsilon 2, and bond transition between 2 and 1. All right, so I'm just ordering all of the R dependencies as we write things down. Right, and then I'm going to split this up because one of the things that we can do is take this dr to the 5th, and we can take the integral over the position of the s equals 1 end of the chain and put it here because all of the dependence on that monomer is to the right of it. Okay, actually we can put it here. And so this is going to be equal to 1/2 integral dr5, dr4, 3, dr2. All of this stuff up to here, right? Yes. And then we'll have integral 5, 4, epsilon 4, I'm sorry, bond transition 4, 3, bond transition 3, 2, epsilon 2, commas in here. Integral dr1, and then bond transition of R2 minus R1. Then again, similar to, I think, an argument that we made last time when we were doing like the non-interacting case. This is just the integral over the position of monomer 1 when it's bonded to R2, but R2 is constant while we're doing this integration. Right? When you have a 2D integral and you're integrating over y at fixed, you typically would do that at fixed x. Right? We're kind of doing the same thing here, except now we're integrating over the allowed positions of monomer 1 while R2 is a constant. Right? So the only functional dependence that matters here is just that on R1. And what we argued last time is that that is 1, and we'll just repeat that a bit. So if you do a change of variables, we'll say R12 is R1 minus R2. And so then dr12 equals dr1. Right? And so these two things allow us to say that the integral of dr1 b to 1 is equal to dr12 b of r12. And this is just the integral of a bond transition probability. So this is just 1. Okay, so that lets us basically get rid of that chain end. And we can apply the exact same logic to get rid of this one, right? We can integrate over position of monomer 5 and get rid of this guy. Right? Because again, this is a bond transition probability. This is the only place where the position of monomer 5 shows up. So we fix R4, do the integral, gives us 1. Right? Right, so we can say similar integral phi dr5 of phi 5 4 is just 1. All right, so we've killed off 2 of our 5 integrals. And so now what we have left is integral dr4, 3, dr2, epsilon 4, phi 4, 3, phi 3, 2, epsilon 2. All right, so we can't use this trick anymore. Now we have to use one of our others. And so I'm going to write this out a little bit with a little bit more detail shown. So dr4, dr3, epsilon 4, phi 4, 3. What do I want? Make sure I get this right. Integral dr2, epsilon of r2, phi of r3 minus r2. Right, so now this guy is a convolution operation. And whatever we do, we're integrating out the position of R2. So whatever result we get is going to be a function of R3. right? And so just for simplicity, I'm just going to call that some generic f, let's call it f sub 3 of R3. And we can write this as the inverse Fourier transform of phi hat of k times epsilon hat of k, right? Because it's a convolution operation. And now we can play a similar game with the next term. Right, so then we will have integral dr4 epsilon 4 integral dr3 b of r4 minus r3. And then I'm just going to write this as f3 of r3. Right, whatever the result of that convolution was, it's this guy. And again, the result of this guy is going to be some functional dependence on R4, right? Because we're integrating out R3. So we'll just call that guy F4, R4. And again, this is inverse transform of phi hat of k, F3 hat of k. And this thing is just the argument of this Fourier transform. And so we can write this again as inverse of phi hat times phi hat times epsilon hat. And all of those depend on k. I'm just not writing it out. All right. So then we have integral dr4 epsilon of r4, this sort of generic function f4 of r4. Right. And this is where we can finally use the other Fourier transform rule that we had, right? Where we write this as the sum over modes, the first function of k times the second function of minus k. Right, so this is now where did it go? Over B, sum over Fourier modes, epsilon hat of k, hat k, sorry, of minus k. Right, and then we can plug in for the Fourier transform of f4, right? And we'll have a phi squared times epsilon, and all of them need to be at minus k. Right, so then finally we have 1 over v, sum over k, epsilon of k, epsilon of minus k. These are all in Fourier space. All right. How do we feel about all this? I'm sorry? This is negative k in the bottom, yeah. And that comes from that original Fourier transform rule that I forget if I just write it down or prove it in the math review thing, but
What
it is
happened
known.
to the factor of 1/2?
Oh, where did I?
Are we just ignoring it?
Oh, yeah, you're right. I'm just going to erase it back here. We'll put it back in when we go back to the double sum term. But yeah, we did lose that factor of 1/2. Sorry about that. Okay. The arguments about integrating over the monomers before the outside of the ones that we're currently considering, is that reasonable? Because that was like one of the stumbling blocks for me for a long time. Like the argument for how I was able to integrate over R1 and R5 to get to the terms that have the fields like that, that was one of the tricks and for me. And then I guess just writing all this stuff in terms of Fourier space as convolutions, that's maybe not the end of the world, but it's well, this sequence of operations I think was maybe a little bit of a trick. Yeah. 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 All right. So I guess the last little bit that we need here. So if you remember, like this, our phi of r, this thing was prefactor and then e to the minus 3 over 2 b squared r squared, right? That was the bond transition probability. And I just did proportional to because I didn't write out the prefactor, but that means that our phi hat of k, it's normalized so that we have minus k squared b squared over 6. I always struggle with my b's and 6's looking a lot alike. So again, if it's ever unclear, don't hesitate to ask for clarification. But again, this is an even function of k, right? So this phi hat of k is equal to phi hat of minus k, right? And so then this whole thing is just equal to 1 over v sum over k. I'm just going to write these as subscripts, epsilon of k, epsilon of minus k. And then basically we have phi hat squared. And since phi hat, sorry, this is phi hat of k squared. And since this is phi hat is just an exponential, we can write that guy out. So sum over k, epsilon k, minus k, e to the minus k squared b squared over 6, and then times 2. And I'm not canceling out the 2 intentionally. I'm sorry? Oh, yeah, they should. Sorry. I will probably eventually drop the hats on Fourier transforms, but for now, I'll try to keep them. All right, and then the pattern that emerges, and I'm just going to tell you this part. If you repeat this whole process for like different choices of M and J, the pattern that emerges is that the thing multiplying here is just the number of bonds between M and J. Right? And you can sort of see that from the way that the combination of integrals shows up. You're going to have one epsilon, then all the bonding transition probabilities in between, and then the other epsilon, right? And everything else is going to integrate out. Okay, so this too is the number of bonds. Right, so in other words, this is equal to M minus J. I think that, yeah, that gives us the right sign. And so the general form that comes for each term, well, I've erased the double sum thing, but the general form that comes for each of the term in this double sum. So each term in MJ, this double sum, has the form so it's 1 over V, sum over K, minus K, then e to the minus K squared, B squared over 6, and then number of bonds separating M and J. All right. So if we're okay with this, I hope, we can go back to the molecular partition function and plug this in for that term. So if we plug into Q, then we will have Q is e to the minus W star N over V. We have the factor of V from integrating out the ideal gas term. We have our factor of a half. We have a V in the denominator from the 1 over V from going to writing this as Fourier space. Then we have sum over M, sum over J. So we're summing over the pairs of monomers. And then we still have the sum over Fourier modes from over there. Epsilon hat K, epsilon hat minus K, e to the minus K squared, B squared over 6, absolute value of M minus J.
Rob, camera check.
What's that?
The first word
Plug.
before
Plug
into.
into. Sorry. Yeah, it just says plug in the queue. Sorry, it got cut off.
So we use the bracket W notation when we set when we do mean field transmission, right?
Wait, sorry, I lost.
So like typically when we started writing Q, we would write Q bracket W with the field, right?
Yes. So no, in fact, I think to write this more precisely, because epsilon is still in principle a spatially varying thing. So really this should be now Q of epsilon. Yeah. Yeah. That's right. And so, yeah, it still has the functional dependence of epsilon that we're retaining for now. And we haven't actually invoked a mean field approximation yet. We've just said that there is a mean field solution, and we're subtracting that from W of R. But we haven't actually invoked the mean field approximation.
Could you say that last part again for me?
We haven't invoked the mean field approximation. We've asserted that there is a mean field solution, and that the variations around it are small. Those are the assumptions, but we have not invoked a mean field approximation exactly. All right, so the final thing that we want to do to get this to kind of a stopping point is get rid of this sum over M and J, right? And this is where we're finally going to take the continuum limit and assume that the chains are very long, and we're going to take these sums to an integral. So now we're going to take the continuous chain limit. So then our sum of m and j, these guys are going to go to integral dm from 0 to n, integral dj from 0 to n. And again, this is just assuming that there's enough monomers that the distinction between the sums and the integrals doesn't matter. All right, and then that's, from there, it's not too bad to solve because we can just write integral dm, integral dj. These are definite integrals, e to the minus k squared b squared by 6, m minus j. The only real subtlety here is that you have to deal with this absolute value, but it's not terribly difficult here. Basically, you just have to break this up into two different terms, one where m is greater than j, and the other where j is greater than m. And then you can write it as sort of normal integrals that you know how to deal with. So we'll say dm goes 0 to n. And then to deal with the terms where m is greater than j, you want to stop the j integral at m. So you'll go dj from 0 to m. And then e to the minus k squared b squared m minus j over 6. And again, this is now an m minus j without the absolute value. And then to hit the other term, you can write this as dj, dm 0 to j, e to the minus k squared b squared over 6, j minus n. You can also just make it twice the first one, and because it's just the same thing repeated. All right. Let me see. So these are just integrals of exponentials. Can you all trust me to just write down the answer, or do you want to see the work? It's okay. All right. So, I mean, hopefully this is at a point where you can believe it, or at least plug it into Mathematica or something. So after some algebra, what you end up with is factor of 2 from the pairs of integrals. There's a prefactor, 6 by k squared b squared. This is all squared. Then there's a constant, k squared b squared by 6 plus epsilon k squared b squared n over 6 minus 1. And then the game that is usually played is that you would multiply this guy by 1. And we're going to define a radius of gyration. Well, the square of the radius of gyration is n b squared over 6. So RG kind of naturally emerges from the combination of variables that ends up in all of this. And so then all of this ends up just being n squared 2 over k to the 4th, RG to the 4th, k squared, RG squared, plus e to the minus k squared, RG squared minus 1. And then this combination of things is the Debye function, the Debye scattering function, or the form factor of a Gaussian polymer chain. So this whole thing just boils down to n squared g hat of k. So G sub D with the in Fourier space is usually it's the notation that's used in Glenn's books for the Debye function. No, this is just this part. Yeah, it's just the double M, the double sum, and the exponential. So Q comes out to be, write that out. And so Q simplifies out to B, and I'm going to distribute the prefactor of V through the thing. E to the minus W star N 1 plus N squared over 2V squared. Then the only thing we have left is the sum over K, epsilon minus K hat G hat D of K. Or if you would rather think about this in real space, we can write it out in real space. So we can say this is also equal to W star N 1 plus still N squared, but now just one factor of V R prime. All right, so that's the main thing. And so this is how you can kind of derive the form factor in this context. And I guess the way to think about this is that we still have this mean field term that's hanging out front, right? Because again, this Q is maybe a little weird. It's the partition function of of one of these Gaussian chains. And then this term is just a correction to the, I guess, chemical potential of this chain that's due to the interactions of monomers at R and R prime, right? That's what the fields represent. They're monomers at two different locations. And then the Debye function tells you how likely they are to be connected to each other for a monomer at R and R prime, right? And so that's kind of the sort of physics that's buried into this guy. And so again, GD is sort of telling you about the shape or the probability of finding two chains at different locations or separated by R minus R prime. And then you have the field interactions at those two spots. Where did I put my chalk? Questions about this? Yeah, Josh. Mm-hmm.
Is it guaranteed that the Gaussian term is bigger than the third or fourth order term? So not
Mm.
so they're not. So.
Yeah, I'm not sure that it's guaranteed. I mean, I think you're assuming it once you start truncating the Taylor expansions of the exponentials, right? But I guess it's not guaranteed. Yeah, I mean, and getting to higher order terms, I think is the big shortcoming of how I approach this stuff, because that's something I haven't yet been able to work out. And I don't know how to do that without doing like the density functional theory type approaches. But I don't understand those well enough yet to be able to teach them. But I think just getting to quadratic order, this is a much easier way than doing the perturbation stuff. No. I hear you. I hear you. Yeah, I'm not sure. I'm really not. And I was actually looking this morning trying to find an explanation of the perturbation approaches that I could actually follow, and I haven't yet. All right, so I guess the other thing that I'll say here, we also know that we had this density operator, right? So there was this rho tilde thing that we defined some time ago. And we said that this was minus n derivative of log q with respect to w. And actually taking this derivative is a little bit tricky because of the way that we've broken w into a constant term and the small corrections. But what you end up with in the end is, I think you can probably understand it intuitively, is that you have this is like the mean field contribution to the density, right? Number of chains, monomers per chain per volume, right? So it's a homogeneous density. This would be like the mean field contribution to the density. So this is the term that would come from the W star part of this. And then you have the fluctuation correction, that's little n big N squared over V, and convolution of the field with the Debye function. Right, and so again, this is homogeneous mean field type of result, and then fluctuation corrections. And the leading order correction turns out to be linear in the field, the small fields in the density, but it's quadratic in the molecular partition function. All right. Any questions about this? All right, well, the other thing I wanted to go through today, and we won't go through all the math in nearly as much detail. I'll just kind of highlight what changes, is the case for the diblock, because one of my goals is to be able to get to the diblock structure factor by the end. So we talked through diblocks a bit last time. Again, just to sort of remind us, we have basically a chain with two different species. We don't necessarily have to get into the types of interactions that we have for this guy. We're just going to say that monomers A experience one field and monomer B experiences another field, right? That's going to be the kind of the key thing. We'll have F is, again, we'll neglect any plus ones that should or should not be there. But they're A and B blocks of the copolymer. So I'll call this guy A, this one B. And really the key difference is that when you go through all of this, is that you have to keep track of which field, which monomer is experiencing. Right, so we have this double sum of M and J that goes over all the monomers on the chain. And now the field itself, right, so the epsilons that are in that double sum, you have to keep track of the index because the field changes when you go from the A block to the B block. And that's the detail that you have to keep track of. Right, so experience, so they interact with different fields. Right, and so the way that you deal with this is that whatever field A interacts with, you're going to say that this is some homogeneous mean field result for A plus a small perturbation that's epsilon A of R, WB of R, WB star plus epsilon B star of R. Right, and then that quadratic term, so you do, once you make this assumption, you have exactly the same arguments through everything. You do the Taylor series expansions of all the exponentials of the monomers interacting with the fields. And then you do the huge multiplication out so that you have all the quadratic terms. All the linear terms are again gone. And what you end up with in the end is a double sum that goes from m equals 0, so over all monomers, j equals 0 to n. But now the fields are going to have indices on them from the monomers. Epsilon hat j of minus k. And then assuming both blocks have the same bonding potential, you end up with something, a term like this. Sorry, I don't know why I put stars on the epsilons up here. They don't need them. And so then epsilon m of k is epsilon a hat of k for m less than na, and epsilon b otherwise, right? So the A block interacts with one field, the B block interacts with the other field. And the same thing is going to be true for epsilon j. And then to get the sort of canonical result, the thing that you have to do is basically break, there's a term like this, but now this thing becomes a sum of three terms. Right? There's one where you have epsilon A and epsilon A in both places, epsilon A and epsilon B, and then epsilon B and B. Right? So you have basically the contribution from how the A monomers affect each other, how the fact that the A's and B's are connected, how those affect each other, there's the cross term, and then how the B monomers affect each other, right? That's the content of those terms that come out. So you end up with so you have three contributions to Q. Right, there's a, so you sum from m equals 1 to na, and from j equals 1 to na, epsilon a hat of k, epsilon a hat of minus k, and then bonding stuff, b squared over 6. Right, so that's the AA contribution, plus we can do the BB next. So we'll start at NA, N. And then for the cross term, so because both sums go from 0 to n, there's two cross terms, one where M is hitting the A monomers and J is hitting the B, and one where M is hitting B and J is hitting A. So we just write that as plus 2 times one of them. So it's from 1 to NA. And J equals NA to N. And so J is greater here, so we can just write that as J minus M without the absolute value. Right, but I'm not going to go through any more of the math of this. I'm just going to write down the answers, but it's the exact same games that we did before. Take the sums to integrals. They go from 0 to their limits. Then you end up plugging back in. And the only thing that's different now is that you end up with modified Debye functions that show up in the partition function. And there's actually 2 of them that we have to care about. So you do lots of calculus. E to the minus WA star times F and E to the minus WB star 1 minus F N. So those are the prefactors, the homogeneous mean field prefactors. And then this is times 1 minus N squared over 2V sum over K. We have a lot in here. So epsilon A hat K, epsilon hat A minus K, modified Debye function that I will define in a moment. It's 2GAB of K. And then plus the B term. Close that and close that. And what we should end up with, let me see. Yeah, so then we'll have this modified Debye function. So it's the one with the subscript D is very similar to what we had before. It's just that F shows up in a couple of places. So this is F, K. The prefactor is the same. So it's 1 over K to the 4th RG squared, but then F K squared RG squared plus E minus K squared F minus 1. And the second one for BB is the same. You just plug in 1 minus F for F. So that's unchanged. And GAB, the cross term, depends on F and K. It's the same prefactor, K squared, G squared. And that's it. All right, so that gives you the weak inhomogeneity expression for the partition function of the diblock. And then this is the thing that we will use to finally, eventually be able to get to the structure factor for a diblock. And we shouldn't need a huge amount of time left to do that. But I mean, kind of the thing that we've done that, you know, if you just sort of step back and think about sort of stat mech of liquids and polymers writ large, you know, we've gone from this many body interaction thing, and we've been gradually, you know, building in all the physics of the polymer connectivity and how they interact with each other with simple models, sure, but it's, you know, we've built in a lot into it. And we're seeing a lot of progress that we can make with analytic expressions. And next time we'll go through how we can actually get to just full expressions for the free energy of the system based on these approximations. Because we've gotten the fields out of the exponentials, right? That we've approximated them, assumed that they're weakly varying. And what we will see is that that actually lets us just analytically solve the path integral that shows up in the partition function and get an expression for the free energy. And so that's something that we'll be able to get through next time. And then once we have that, we'll be able to, and we know how to deal with those path integrals, then we'll be able to get density correlation functions pretty easily. And that'll turn out to be relatively quick. All right, any questions about any of this? At some point, we'll talk through how to deal with like different polymer architectures and stuff like that if you have branching and things like that. But it's, again, if you can follow this, you can do basically any of it. This should set you up to be able to do a lot. All right, well, we will resume on Tuesday and we'll talk about the Gaussian integral stuff. All right, thanks, y'all.